Hi, on behalf of my co-authors, I'll present in this video our work crafting research products through digital machine embroidery. It is known that creating soft wearables is complex because it combines challenges from many sides. There's technology, instruction design, fashion, the specific context of application. As designers, we are invited to apply and develop techniques and knowledge that are outside our traditional range. That often means that we work iteratively and we increase the complexity and the levels of fidelity of prototypes as we go, often relying on manual fabrication. This way of working presents a few challenges. One of them is the possibility of comparing our prototypes. Due to their varying levels of realization and inaccuracy of the reproductions, that's quite difficult to do. Another point is that about the fidelity of our prototypes is that the conditions into which we are going to be testing and actually using them are on the moving body. And that demands a high level of fidelity in terms of aesthetics and the material properties that maybe other prototypes might not require. To achieve those high levels of fidelity and so on, it does require quite a bit of skill. And while examples of interesting wearable concepts and applications are abound, there's still little guidance for design researchers as to how to realize such prototypes in a high level of detail. Therefore, as a community, we need to develop guidance and disseminate knowledge for how to make use of relevant fabrication techniques to support the development of soft wearables as research products, prototypes of high level of finish and detail. In our work, we explore the potential and the implications of using digital machine embroidery to craft such types of prototypes. We chose this technique because of its versatility. Digital machine embroidery has been used in HCI in many applications to create soft circuitry, different types of sensors, actuators, and so on. We argue that it can also enable the fabrication of reproducible research products, supporting very hands-on processes. To do so, in our process, we use the machine to create the textile substrate together with integrating or embedding electronic components through a unified process, whilst keeping high control over alterations between prototypes. This freestanding textile substrate is created by means of a technique called chemical embroidery, in which the design is embroidered in a water-soluble stabilizer, like what you can see in this picture. Once this stabilizer is washed off, you're left with your textile. We demonstrate this approach through the case of the Smart Sock, sock that was developed as part of a bigger research effort that aimed to develop solutions for the recovery of trauma patients with surgically treated fractures of the lower extremities through early weight bearing. This project was developed between 2015 and 2017 through the collaboration of many departments between Maastricht ID, the Academic Hospital Maastricht University, Adelante, and Eindhoven University of Technology. The aim was to develop a system that would measure several parameters related to weight division, unwinding of the foot, and indicators of overload, which are typically evaluated in clinical practice. To do so, the system would compare data from the pressure sensors on the sock worn on the affected foot to each other, as well as with the ones on the other sock. Therefore, the reproducibility of the design and the sensor alignment were very, very crucial. Our design process, thanks to this technique, was very highly paced, resulting in 2 proofs of concept, 2 prototypes, and 7 research products. The proofs of concept were constructed using off-the-shelf materials and components with the purpose of determining the number of sensors and their location under the foot. Based on them, it was defined that each sock would contain 5 pressure sensors and 1 accelerometer. Both prototypes and research products were fabricated through the digital machine embroidery. And in terms of the embroidered elements, they were very similar. The difference was their function. The prototypes served to explore the fabrication technique. And the research products, they were used to collect data to develop and validate the algorithm. By undergoing this process, we experienced how the use of this technique of the digital machine embroidery can be a strong tool for crafting soft wearables. As the main advantages, we recognize that it is first and foremost a low entry fabrication technique, both regarding skills, so that makes it quite friendly towards non-textile experts, but also equipment, because you can get similar levels of sophistication in your outcomes using both domestic or more advanced semi-professional machines. The stability of the embroidery frame and the accurate positioning of the needle are quite helpful in general for creating applique techniques. And in the case of these types of prototypes, it can also be very helpful for embedding components during the sewing process. The freedom of routing, which is crucial for the creation of soft circuits, but it was also in our case proved to be very supportive in exploring the qualities of the substrates. And of course, the reproducibility, which allows us to have high control over small alterations between designs, which on one hand gives us kind of a freedom to explore while knowing that we can recreate the results that we are interested in or go back to what we had before if they don't pan out. And lastly, the unification of the process, creating the textile substrate in the finer shape together with the integrating technology, which reduced the burden of constructing garments. A big aspect of our approach was also identifying the techniques and the design elements that we could use in our prototypes. The embroidered elements that we use in our prototypes and research products included substrates, support pads, placeholders, conductive traces, contact pads, sensor components, and insulation. The three most significant elements were obviously the sensor, for being the most relevant to the main goal of the project, the contact pads, because as much as they are very simple and obvious, they very much facilitated our high pace of our process by allowing us to easily attach and detach a control unit that contained the bulk of the electronics, so that we could test different prototypes. And for us, the most interesting, the substrates, which were embroidered in the final shapes of the prototype parts, simplifying the fabrication process and opening up opportunities for exploration. We found that by changing some sewing attributes or layering design in certain ways, we could influence the material properties of the embroidery, both globally or locally. And we could create some material behaviors like stretch, for example, by doing so. We observed a few implications of using embroidery as a means of crafting research products. And we narrowed them down to three aspects: sensor alignment, layering and manipulating fabric character, and shaping and construction. In terms of sensor alignment, as we mentioned before, this was a very key point for the project, so that the sensor readings for both feet could be comparable. Our approach allowed exploring and changing different aspects of the designs through an integrated solution, while still preserving the relative position of the sensors. Changes made could serve to optimize designs, explore the aesthetic and material properties, include new components. As you can see in the example of the picture, for example, there is a PCB that was added on Research Product 1, or to investigate the performance of various sensors designs, which was what happened mostly in this project. The great advantage we found in the embroidery is that you can layer up. If you see this image, you have different layers on top of each other, but in the end, they look and behave as one. So we found opportunities for manipulating this behavior and to add functions to the substrate locally, like using a patch as a support pad that can protect the PCB and prevent its interconnections from getting loose. These are some things that we'd like to further explore, and as well as what would be the effects of different yarn choices, which we only briefly investigated by reproducing some of our prototypes in other kinds of thread. And it would be interesting to see what they would do to the material properties of the substrates so that we can better understand how to design them. Lastly, shaping and construction. Shaping was a very important part of our process since the substrates are, well, in fact, shaped as soles on the machine. Similar to other digital fabrication techniques, a limitation of this one is that you have the work envelope. If we were not limited by the maximum sewing area of the embroidery machine, or if we were willing to trade accuracy for size, Perhaps it would have been possible to use our insights on material properties to further explore shaping the full wearable at once, rather than in 3 separate parts, as you can see above. Well, actually more if you count the top sides of the electrodes, but the form factor itself was done in 3 parts. To conclude, through the case of the Smart Sock, we demonstrate a path for creating soft wearables in the form of research products by means of digital machine embroidery. Our experience shows promise in further exploring how to design the material qualities and properties of freestanding embroidered substrates, which opens up opportunities to research end-to-end fabrication of wearable research products. Future steps could include moving forward towards a design language of digital embroidery, and to further engage with the investigation of how to manipulate material properties of the embroidered substrates. We'd like to finish by thanking the multidisciplinary team involved in this project. It was a great process, and I'm very thankful for everybody who participated. If you're interested in knowing more about our work, please have a look at our paper and contact us if you have any questions. Thank you for watching.